Okay, this is exam 4 for fall 2017. What is the total kinetic energy of this thing? Well, the total kinetic energy includes translational, 1/2 mv squared, plus rotational, that's 1/2 I omega squared. The translational is easy. It's 1/2 times 8 kilograms times the speed, which is 2 meters per second, squared, plus we need to know what is I. For a disk or for a cylinder, it's 1/2 mr squared. That's 1/2 of 8 kilograms times 0.5 squared. That's a half of 8 is 4, quarter of 4 is 1. So I is equal to 1. So I'm looking at 1/2, 1 kilogram meter squared, times the speed is already in radians per second, 4 radians per second, squared. So that's 4 times 4 is 16 plus 8, which is 24. Merry-go-round moment of inertia rotates at a constant speed. Kid jumps on, and the moment of inertia goes up to 2I. Well, we know that I omega, that's our moment, that's our angular momentum, that is conserved. And so if I goes up by a factor of 2, omega has to go down by a factor of a half. But I want to know actually what happens to the rotational energy. And the rotational energy is 1/2 I omega squared. So now taking what I know that I goes up by a factor of 2 and omega goes down by a factor of a half, I have 2 and then I have a factor of a quarter. So 2 times quarter, that's equal to a half. So the total energy, the rotational energy, is going to decrease by a factor of a half. And that energy is lost by the frictional force that acts on the kid. It actually does work on the kid, slowing them down. I need to rank these by their moments of inertia. What A has the most mass out at the biggest radius, so A is the biggest. Oops. And then I need to rank B and C. Well, they're not the same, so I can get rid of A. Looks like B has more mass out at bigger radii. C doesn't have that. So B is the next biggest and then C. So C is the right answer. Imagine a solid metal sphere, radius 2 meters and mass 3 kilograms. You attach the sphere at one end of a lightweight 6-meter long cord and twirl the sphere around your head. Which expression below gives the best estimate of the moment of inertia? Listen, some of you put this or this thinking that, well, this is a sphere plus a particle. But in fact, this came from OpenStax. It's really just like a particle. That the fact that it's a sphere is not consequential. So it's just going to be A is the right answer, not C or E or B or D. A is the right answer. You treat it like an individual particle. And here's some more particles here. So I want to know the moment of inertia here. It's the sum of mr squared. That's the sum of 1 kilogram times 1 meter squared plus 1 times 1 squared plus 4 times 2 squared. So that's 1 plus 1 plus 16. That is 18 kilogram meter squared. Bar spins about its center of mass. Let's see, I want to know the angular speed. There's no forces here. I don't speak of any forces or torques. So that would clue me into thinking that this is a momentum problem. And indeed it is, that I have conservation of momentum, that I omega initial is equal to I omega final. I need to figure out what is the moment of inertia. So I is 1/12 mb squared. I'm going to work this a different way in just a second to show you how an easier way, but let's do it this way first. So initially, it's going to be not 1/2, 1/12 mb squared. It's a bar spinning about its center. That's going to be 4 times 3 squared. So initially, I is 4 times 9 is 36. This is equal to 3 kilogram meter second squared, and the rotation rate is 2 revolutions per second. And then final is going to be the final, this is initial, I final is 1/12 of the mass is still the same, times 6 squared. So that's 4 times 36 divided by 12 is going to be 12. So this is equal to 12. So it's going to be 12 times omega final. And then I solve this for omega final. It's going to be a half a revolution per second. So 6 is A. But listen, an easier way to do this is to say, well, gosh, I is 1/12 mb squared. I am increasing my length from 3 to 6 meters, so I'm increasing it by a factor of 2. That means if I increase B by a factor of 2, I decrease this by a factor of 4, or I increase this, rather, by a factor of 4. And so if I goes up by a factor of 4, then that means this has to go down by a factor of a quarter. And indeed, it was 2 revolutions per second. Now it's going to be a quarter of that, which is a half a revolution per second. Okay, what is the net torque about this point? Well, recognize no torque there because theta is equal to 180. So my only torque is given by this force, 10 newtons at 1 meter moment arm. 10 times 1 is 10 newton meters clockwise. And indeed, it is a clockwise rotation. Now, I also want to know what is the angular velocity after 2 seconds. Well, first, let's find out what I is. It's 1/12 mv squared. The mass is 3 times 2 squared. 2 is just the length of the rod, B. That's 3 times 4, that's 1 kilogram meter squared. And then I know the torque is 10, so I can figure alpha is going to be torque over I. This is just from Newton's second law, so it's 10 Newton meters divided by, actually it would be negative 10 Newton meters because it's clockwise, divided by 1, so it's going to be negative 10 radians per second squared. Oh, this 1 came from kilogram meter squared. And then I want to know what is the angular velocity. So omega is equal to omega naught plus alpha t. We're assuming that it starts at rest, and so it's going to be minus 10 times 2 seconds minus 20 radians per second. So B is the answer for number 8. Now number 9, 2 children push on opposite sides of door during play. Both push horizontally and perpendicular to the door. One child, here's the door, there's the axis of rotation. One child pushes with a force of 20 newtons at half a meter. And the other child pushes over here at 1 meter. What force must this be? Well, you say F times 1 equals 20 times 0.5. Balance the torques out. 20 times 0.5 is 10, so F is 10 newtons. Rank these torques from greatest to smallest. Well, this one has a small force. This one has a force that's roughly twice that, but a moment arm that's half the moment arm up here. So since torque is equal to Fr sine theta, though theta is the same for both of these, one has a big force at a small moment arm, one has a small force at a big moment arm. So A and D are going to be the same. Oh, that can give me the answer right there. And then C is bigger than B because this angle is 90 degrees. Or yeah, that angle is 90 degrees. So sine of theta is equal to 1 for that one. Boat has a total mass of 3,000 kilograms. What fraction of the boat is submerged? Well, I know that the buoyant force in this case, in order for it to float, has to be equal to the weight. So the buoyant force has to equal 30,000 newtons because it's 3,000 times 10. That's the weight. So the buoyant force is also equal. The buoyant force is also equal to the weight of the displaced fluid. So the buoyant force is equal to the density of the fluid, volume of the object, times g. And this is equal to 30,000 newtons because it has to be equal to the weight. And now I can solve for the volume of the object. That's going to be 30,000 newtons divided by the density of the fluid. Well, this is water. It has a density of 1,000. And g, which is 10. So it's going to be 30,000 over 10,000, or 3 cubic meters. Now that's the volume that is submerged. But notice here that the actual volume, the total volume, is equal to 3 by 1 by 3, which is equal to 9 cubic meters. Only 3 cubic meters is submerged, so that means 1/3 of it is submerged. What is buoyancy? Well, buoyancy is an upward force. So I can get rid of these two. It's not exerted by a solid. That's not true. It's actually exerted by a fluid, and it opposes the weight of an immersed object. Where is the fluid's pressure highest? Well, the pressure is highest where V is small. Remember, that comes from Bernoulli's principle. And V is small here and big here by the equation of continuity. So the pressure is highest in A. Bernoulli's principle says which of these? That energy is conserved in a flowing ideal fluid. This right here, it's sort of pascals, but it's not always true, but it's sort of pascals. It's based on pascals. This is Archimedes. This is equation of continuity. And this is pascals. Again, A is just an incorrect statement, but it's based on an incorrect understanding of Pascal's principle. Okay, this was from OpenStack. So blood passes through the capillary bed in an organ. The capillary is joined to form venules. If the blood speed increases by a factor of 4, and the venules have a total area of 10, what is the total cross-sectional area? So when blood goes from venules to capillaries, it slows down. And similarly, here we're going from capillaries into venules. Now, I'm going to draw it like this, because this is sort of the idea that we have. Where over here I have the venules, and over here I have the capillary bed. Now, we know that the capillaries are actually broken into a bunch of little pieces, but if you put them all together, the idea is that they form a cross-sectional area that's bigger than the venules, just because there's a lot of them. Okay? So the total cross-sectional over here is 10 centimeters squared, but I have a speed that is 4v over here. That means that the area over here is going to equal to 4 times that, or 40 centimeters squared. I have v over here. So if I really wanted to think about this in terms of an equation, I would say a1v1 equals a2v2. a1 is what I'm looking for. v1 is equal to v. a2 is 10. v2 is 4v. The v's cancel. a1 is equal to 40. That's 15. Okay, this was from OpenStax too. I'm not going to read it to find the density. I say the mass over 92. And 260 over 92, that's about 3, so B is the right answer for 16. Scissors hydraulic lift. The area over here is 0.01. The area over here is 1.2. I use Pascal's principle. F1 over A1, that's the pressure on the left side, is equal to the pressure on the right side, F2 over A2. So I'm looking for F1. So I'm going to have F1 over, what was it, 0.01 is equal to F2 is going to equal to the weight of this car, which is going to be 1,000 times 10, or 10,000 newtons, divided by A2, which is 1.2 meters squared. Now my area has increased by a factor of 120. So that means that my force is going to decrease by a factor of 120. So solving that I get F1 is equal to 83. Okay, this figure shows a manometer. It's filled with mercury. The pressure is 1 atmosphere. So I have pressure 1 atmosphere, which is 1 times 10 to the 5th pascals. Excuse me, I need to pause this for just a second. Okay, sorry about that. So let's see, we have this manometer and it has 1 atmosphere and the height here is 5 centimeters. I want to know the pressure that is right here. What is that pressure? Well, first of all, I know this pressure is less than 1 atmosphere, and I know because of the relative heights of the liquids that if it was more than 1 atmosphere, it would be pushing this level down to a level down below the height of the left-hand side. So my pressure then is going to equal to P naught minus rho GH, because I know that P is less than P naught. What I could stop there, right? Because P naught is 100,000 minus rho, which is 13,600. That's the density of mercury times 10 times 5 centimeters, which is 0.05 meters. And then that's going to be 93,000. Square bucket contains 3,000 milliliters of water. It has a base with the dimensions 0.5 by 1 meter. What is the pressure at the bottom of the bucket? Well, pressure is equal to F divided by area. And I have a total force that's equal to the weight of the bucket. And then that's going to be divided by the area. Let's do the area first because that's the easiest. The bottom of this bucket has an area equal to 0.5 meters by 1 meter. are, you know, half a square meter. The force is going to be equal to hold on. I'm sorry, let me pause for just a second again. The force is going to be equal to the weight of the water. And this was a little tricky to get this. So you have to know the force is equal to the weight of the water, which is m times g. And so I need to find the weight of the water. Well, 3,000 milliliters, that's 3,000 cubic centimeters. And I know that the density of water is 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. So you could do it in kilograms and cubic meters, but you need to do some unit conversions. Unit conversions that I provide to you in a couple of questions, but let's do it this way right now. So these cancel, and so this is going to be 3,000 grams. 3,000 cubic centimeters of water, 3,000 milliliters of water, 3,000 grams. They're all the same because a gram is a cubic centimeter, or rather, a cubic centimeter of water has a mass of 1 gram, and a cubic centimeter and a milliliter, they're exactly the same. So 3,000 grams, and that's equal to 3 kilograms. So I have 3 kilograms times 10 meters per second squared. That gives me the weight. So 30 divided by a half, that's going to be 60 newtons per square meter. So C is 19. Which state are molecules or atoms the closest together? Well, they're the closest together in a solid. A fluid is a liquid or a gas, so they're going to be further apart than that. And then, of course, with plasmas, they're basically a gas, right? They're an ionized gas where the atoms are separated. A tendon in your arm has a length there. Using Young's modulus, let's just go ahead and write the equation down. F over A, that's the stress, is equal to the Young's modulus times the strain, which is delta L over L. And I'm looking for how much does it stretch. I'm looking for this quantity. So my force is 100 newtons. The area is 7.5 times 10 to the minus 5. There's my Young's modulus, 2 times 10 to the 7th. Delta L is, well, I'm looking for delta L. L is 0.1 meters. And so I solve this for delta L, and delta L is equal to 0.7 centimeters. Oh, that's 0.007 meters, which is 0.7 centimeters. So C is the right answer for 21. Calculate the number of moles in a 1 liter volume of air in the lungs of the average person. Air temperature is given. Oh, air temperature, that's not. Oh, wait, no, I'm sorry, it is relevant here. So, ideal gas law, PV is nRT. The tricky part with this is getting all the units right. So, the pressure is 1 atmosphere, which is 1 times 10 to the 5th pascals. Everything's got to be in SI units. 1 liter is 1,000 cubic centimeters, which is 0.001 cubic meters. So I give you that unit conversion, which you could have used a couple of questions ago if you wanted, or you could have done it the way that I did it. I'm looking for N, 8.314. That's what, joules per mole Kelvin, which is going to key us in that the temperature, we need to convert it to Kelvin. And so the temperature in Kelvin is equal to the temperature in Celsius minus 273. Just 236. Is that right? Sorry, it's late today. I don't think that's right. Hold on, I'm sorry. Give me just a moment. All right, yeah, I'm sorry, I made a mistake here. So this should be plus 273, which is 37. That's 280, 310. Is that right? Sorry, I said a 310 Kelvin. Okay, and then we solve for the N, and N works out to be 0.039 moles. So A is the right answer. 2 identical cylinders are at the same pressure, contain the same type of gas. One has 4 times, which has the higher temperature. Well, PV is equal to nRT. They have the same pressure. They're the same container, so they have the same volume. The thing, and the ideal gas constant is the same. I want to know which has the higher temperature, the one with the lower number of moles. And so the one that has the less amount of gas is B, so 23 is B. You have a copper rod that's stuck in a concrete block. Which of these is the best solution to remove the block? So we have copper and concrete. Let's look at those coefficient of linear expansions. Copper is 17, concrete is 12. Copper is 17 and concrete is 12. So this is 17 times 10 to the minus 6, and this is 12 times 10 to the minus 6. These are in degrees Celsius, inverse degrees Celsius. So my copper rod, this is concrete. I have a copper rod that's stuck into it. Let's think about this. If I heat it up, the copper is going to expand at a faster rate than the concrete. So instead of becoming unstuck, it's just going to get stuck more. So heating it up, which tends to be the thing that we do, that's not going to work. If I heat the copper rod, the copper is going to get bigger. And if I cool the concrete block, the hole in the block is going to get smaller. However, if I cool the copper rod and the concrete block at the same time, like put them in liquid nitrogen or whatever, the hole in the concrete will get smaller, but the copper rod will get smaller more quickly and by more. So C is the right answer. Kelvin scale is based on which of these? Absolute zero and the triple point of water. So B. And room temperature is defined to be about 77. This temperature in degrees Celsius and in Kelvin is 25 and 298. That's 273 plus 25. What are you going to do? You're going to do all these things. So D is what all of you put, actually. There's all the answers, though you can find it online as well.